Thanks for coming on a Friday. So just as a Formula One champion pushes their car to the limit, AI workloads are pushing the limits of scale and speed. And one second, there we go. Debris on a track can cause a crash, even for the best champions. And network cards and links that flap are causing AI workloads to crash in GPU clusters today. So I'm Lerna, I'm a solutions engineer at Clockwork, and we are a small startup, and we work on network acceleration software for our customers. Previously, I was a solutions architect at AWS for 3 years, and before that, really at heart and in practice, I'm an infrastructure engineer for 17 years in financial services companies. And there, I enjoyed working on problems of scale, such as centralized authentication systems, low latency monitoring application for all servers in the firm, distributed caching for investment management portal. And if any one of these things went down, then I got a page 3 a.m. in the morning, and I like to sleep. So this type of problems of scale require solutions that are highly available, scalable, and resilient. So today, I'll be talking about similar challenges for networking when it comes to AI ML workloads. And we will look at demos, as well as learnings of a solution that provides resilience against flapping, and so that our AI workloads can run at full speed, just like a Formula One champion's car. So first, I talk about my background. I'm more on the infra side. What about you folks? How many folks here are more on the application side, maybe AI ML engineers or researchers or scientists? I see maybe 3, 4 hands. How about the infrastructure side of things? I see more hands. All right. Hopefully there's something for both sides. So this is my quick agenda. First, it's going to be AI workload layers very quickly. We have the workload on top. It's built using libraries and frameworks. If you have a large enough job, then you need inter-GPU communication. For that, use collective communications libraries like Nickel or RICL. At the bottom, you have the network card that needs to be RDMA capable, and it speaks over fabrics like InfiniBand or RoCE v2. So what are the demands of these workloads from their networks? I want to take a step back. I think we all, a lot of us come from traditional networks side, and traditional networks to me are like big cities, like with busy streets. You expect delays, you get packet drops, and you get tail latencies for your applications. And you basically get best effort service. While AI networks are like high-speed racetracks, and they are built for lossless transmissions. Here you get minimal delays, and you get best performance. Now, in traditional networks, you get network cards that operate typically at 25 gigabits per second or less, and you want to keep those pipes not congested, so you have a safe link utilization rate of 50% or less. Otherwise, you get more packet drops, more tail latencies for your application, and a lot of angry customers. AI networks, on the other hand, can go all the way up to 800 gigabits per second for network card speeds, and you typically get like 95% or more link utilization for like distributed training jobs, so these workloads are running all the time. Now, if you were to profile an LLM training job, then you would see that it consists of cycles of compute followed by communicate for each and every iteration. And if you look at overall job completion time, you'll see that 30% or more of that is actually consisting of this networking part, the communicate part. Now, if I look at an all-reduced operation, it's in a nickel ring. Basically, components of the sum, they're going around. So each and every node, each GPU has the total sum at the end computed, and then they need to pass that sum around, so each and every GPU has the total sum. Now, the finish time of the operation is based on the sum of the latencies within the ring. So to me, this is like a pit crew. In a pit crew, you have different teammates, and basically, the speed of the crew is dependent on the slowest team member. Now, GPUs, they're not going to synchronize. They're not going to proceed to their next step until they synchronize all of their partial results. Everybody has, computed and got the total gradients at the end. So the slowest team member is determining the speed of the team, and slowest flows or nodes are determining the throughput for the AI workload. And we're going to see that in a demo, so it's going to be very kind of clear. And just under the hood, looking at the collective communications library, what's happening there. So you have a sender node and a receiver node. You have 8 GPUs and 16 logical network cards. So in that pink layer, collective communications library layer, GPUs are generating messages that are split into chunks that are mapped to queue pairs. Queue pairs are just like sockets. The network card takes this, packetizes it over the fabric like InfiniBand or RoCE v2, and then the receiving NIC takes that up its stack to the receiving node. So what are the challenges that we see in AI networks? And we speak to GPU cloud operators and their customers, or just companies that own their own GPU clusters. So the first challenge that is not too close to heart, like people don't care about this too much, is lack of visibility. So this is one of the teams that we work with, and 6 months prior, they had a switch that had downlinks, but they didn't realize that 6 months later. That was kind of late. Not only that, but they didn't know why did this happen. So we believe that this is happening because teams don't have access to fine-grained metrics. They only get access to aggregate level metrics, so they're unable to identify and diagnose connectivity issues and resolve them quickly. So this is our foundational research. We're out of Stanford University, and this is a Usenix paper that talks about it. It's a software-based clock synchronization that is probe mesh-based, and it is high precision. And most importantly, it measures one-way delays accurately. You want to know one-way delays. In fact, you use this every day when you use Waves or Google Maps. Like, this is how you know if a congestion is upcoming, for example. So in this first demo, we have 4 nodes. 2 of these nodes are in one rack. 2 of these nodes are in an adjacent rack. And here I have 16 network cards. They are looking healthy right now because of my probe mesh configured probe delay is 5 microseconds. And if I look at one-way delays in between 2 network cards within the same rack in between these 2 nodes, I have 4 queue pairs, and I'm getting about 850 nanosecond per queue pair right now. I don't have any workloads running, so everything is looking the same in terms of the delays. And if I look at one-way delays in between these 2 nodes across racks, then they are looking about 3.2 microsecond range per queue pair. And you can think of queue pairs as sockets or flows. And right now, I don't have any workloads running, so this is just the cluster at rest. But what I'll do is I'll start a workload. And it's just an all-reduced job. It's a pretty simple job that's going to get kicked off in between nodes 4 and 6. So I should see the throughput for those 2 nodes go up. And right now I'm getting 1.38 terabits per second for these 2 nodes. This is not great. I have network cards that are 100 gigabits per second. I should get more than this. There is some congestion contention happening in my cluster, as indicated by those red network cards, which we'll look at next. My network cards are only able to do 86 gigabits per second, not ideal. And if I look at the one-way delays just to show before the workload and after the workload. So before the workload, about 3 microseconds per queue pair, and after I started the workload, I'm getting about 4.1 or 2 microseconds per queue pair. But if I look at these slow network cards with the slow edges, the red edges, that will tell me the story of why. So some of these queue pairs, like that queue pair right there, is having 43 microsecond one-way delay, which is much higher than the rest of the queue pairs. The other 3 queue pairs are getting about 2.6 microseconds. So there's some really slow flows, just like those slow team members in the pit crew that are slowing down the throughput. That's why I'm getting less throughput, 1.38 terabits per second for this workload right now. And it will be a similar story for the rest of them. The next issue is actually quite close to heart because I think people are getting paged about this. There's angry customers and so forth. So this is the visible challenge right now, which is the links that are flapping. You know, in this case, for this customer, I think it was over 10 times within the past hour, and they had to send technicians to swap out cables. And this is common in large clusters, and it's happening due to overheating of optical transceivers or dust particles that you need to clean up. And when it happens, it causes the workloads to crash. And you have to fall back to a previous checkpoint and start over, so you're losing time and you're losing money and efficiency out of the GPU cluster. So I don't know if this is a fair question. How many people work with GPU clusters? Maybe not many. Okay, oh wow, all right, cool. So if your cluster had a personality, which would it be? Would it be the flapper, constantly flapping links and network cards? Would it be the ghoster, drops connections without warning, or the Zen master, always stable? Yell out something, or we can go flapper. None. Ghoster. Oh, there's some. Okay, I saw 2. The Zen master. Anybody? Okay. Yes, none. Okay, yeah, from my experience, interesting that there's more ghosters than flappers, so that's interesting in this room. Maybe we should talk after the talk. And so in my experience, I've seen a lot of flappers in the field, and people are trying to get to Zen masters.
With flapping, you mean fluctuate?
The links just go away, disappear for like maybe 10 seconds, and then come back. But that's enough for, in fact, we will see this in the demo, to cause an issue for the workload. So this is actually the flapping demo where I'm going to simulate the flapping. I first start like a workload, all reduced job, standard job, just to start at the baseline. And I want to see the throughput go up for those 2 nodes, just so we see where we are for the baseline. So in this case, I'm getting a good throughput, 1.47 terabits per second. This is what I should get in this cluster. I have 100 gigabits per second network cards. I'm going to simulate that network card failure, take it down, and it's that first network card, NIC1 in the node 4, the first node on the left. So my workload crashed actually immediately as I took down that network card, the workload crashed. You can see all my network cards are no longer carrying meaningful traffic. And I can see the network card is gray now. It's detected as down. And if I bring it back, so the card is going to come back in a second, like it just became green now. So I detected that it is back, but the workload is not coming back. So this is exactly what happens in GPU clusters today. This is an actual issue where you have to fall back to a previous checkpoint, load all the data, all the weights into the GPUs, and start over from that previous checkpoint if you took one. And just to show you that I'm not lying about that network card truly being up, the card is up because I can see probe traffic. I can see the probes are back, and I can see the duration for the downtime in there on the left. So I know exactly that my card is for sure back, but the workload didn't come back. So here I have 3 runs on Oracle Cloud. The first is the Zen master. There's no failures. So this is just the baseline, 1.47 terabits per second. It's in a similar cluster as what I showed you in the demo. The second is the flapper. So you have it's the same as the demo. The network card fails, the job dies, the network card revised job doesn't come back. So you have to fall back to that previous checkpoint. And the third is about a solution that provides resiliency against that NIC failure. So the NIC fails, your throughput goes down slightly. The reason for that is you lost one network card, so the remaining network cards, they're doing double duty. So you have slightly degraded throughput, but when the NIC is rewired back, you get back to original throughput because all the network cards are doing normal duty. So the learnings from such a solution is that you get a choice of when and if to fix this flap NIC. Maybe you want to continue in that slightly degraded state, and that's fine enough for your requirements. Or another option is you can run until your next checkpoint. At that point, you can fix this flap NIC so that you don't have downtime. My last demo is about congestion. So I'll start again with that baseline state. So I'll have an all-reduced job running first, just so we see that throughput. So it gets 1.47 terabits per second, which is good, very good for this cluster. But I'm going to mess with that job because I'm going to start another job. And this is an all-to-all job. And these are two cross-rack jobs, so they are going to contend at the spine layer flows. Previously, we were getting 92 gigabits per second out of the network cards. And we were getting 1.47 terabits per second for the all-reduced job, but now we're only getting 839 gig versus and 495 gigabits per second for those two jobs. So, and our network card's only doing 51 to 31 gigabits per second. Our throughput went down by about 50% or less, and this is the reason why the culprit is these one-way delays for some of the queue pairs. A lot of them are at the 5 microsecond-ish range, but it goes all the way up to 50 microsecond range, and that is way too high. So we have some very, very slow flows that are taking down our throughput by almost 50%. And the network tells us the same, that it is indeed congested because we get these ECN, explicit congestion notification. So basically, this is in a test bed, and it's showing something similar where I have an all-to-all job, and this test bed, I have 100 gigabits per second node here, but I'm only getting 84 gigabits per second. A lot of the queue pairs below, the one-way delays are in the maybe nanoseconds or microseconds range, low microseconds, but some of them are 50 microsecond range. If I introduce another all-to-all job, then both of these workloads are getting 50% or less than what they could get. Because you have a lot of contention on the wire, you basically have some queue pairs that are getting 100 and 150 microsecond one-way delays. That's pretty bad in slowing down everyone. And the last one is basically a solution that shifts the bytes from congested to less congested paths. And the effect of that is reducing those one-way delays. So you don't have a wide range from like 5 microsecond to 50 microsecond, but you minimized it. Maybe you brought it down, so everybody's running at the same speed at 16 microsecond, let's say. And when you do that, that has the effect of increasing the throughput to higher than what it could be, closer to that line rate for both of these workloads at 92 gigabits per second. Here's your chance to have a magic wand for networking. If you could get a magic wand for networking, and if you could eliminate a networking pain, which ones of you would vote for no more link flapping? 0 votes. Oh, 1. I got 1. Okay, great. How about infinite bandwidth? I got 1, 2, 3, 4, 5 people. And self-healing network cards. Whoa, I got a lot of 1, 2, 3, 4, 5, 6. Very good. I give you each a magic wand for your networking pains. And here are my key takeaways. Lack of visibility when it comes to basically down to the queue pair level is slowing down diagnosis when it comes to connectivity issues. Network cards and links flap in GPU clusters today, so we want to make sure we checkpoint according to our business requirements so that we can recover from them. And delays in those slowest flows, they are actually degrading throughput by as much as 50%, as we saw in the demo. Thank you very much for coming to my talk. Any questions, comments? Okay, yeah, I have some.
I have a question. Do you see those measurements also while the training runs? Or can you see those measurements? Or how does this work?
I can speak about it later, but yeah, there is some future work that we're looking at to do that as well. Yes, yes. Any other questions? Okay, all right. Thanks, everyone. Oh, yeah. Okay, go ahead.
The IP mesh dashboard you used is from Clockwork.
Say that again.
The IP mesh dashboard that you used is from Clockwork.
The demo is, yeah, our demo. Yep.
Oh, okay.
Yeah, yeah. But it's all Grafana charts and so forth. Yeah. So that's all. Okay. Any other questions? Okay. Thank you.